Okay, so now we're on to the exciting part, right? 2D elastic collisions, right? So if we have worked in the lab frame, right? If we attempted the question in the lab frame, we're gonna get a very monstrous quadratic equation, right? And so the conservation of linear momentum would be the first two equations over here. Then the conservation of kinetic energy equation would be this 110 over here. But we can see that it's really hard to work with this. And worse still, right? Currently we have 4 unknowns, but we only have 3 equations, which means that we're actually lacking some information, right? And it turns out the fourth equation will come in the form of relating any of these two variables, right? Relating any of them. And it could come in different forms. So a very simple example would just be um, the velocity of A, right? Putting a condition on the direction of the velocity of A. And if you try to solve equations 108 all the way to 111, right? I didn't solve it myself. Theoretically you can solve it, right? If you give me 1 hour, I can probably do it, but it'll be absolutely monstrous, right? So that's generally not the approach we want to take. And how do we get around this? Turns out in the COM frame, right, things are really nice. Okay, so in the COM frame, remember what were the results that we derived, right, for elastic collisions? We derived that for the elastic collisions in the COM frame, right, the initial and final velocities, right, they have the same magnitude, right? So for both A and B, the initial, which is U, and the final, which is V, the vectors have the same length. Um, and and another result we derived was that the the velocity of A and the velocity of B, right, initially, right, UA and UB, they are only related by a negative of some scaling, which means that they are essentially parallel or anti-parallel. So if this is UA, right, then UB will be something like that, right? Some scaling of UA. It could be larger, it could be smaller, but important point is that it's just a flip and it's just a scaling, right? It doesn't point in a different direction. And why is this useful? This useful is because actually this section, although it's really remarkable, right? 2D elastic collision sounds like it's a lot of work, but actually we did all the work in the center of momentum frame section, because with these four results, right? With these four results, we really have a very nice geometrical picture for what happens in the center of momentum frame. And that is that when two objects bounce off each other, right? So two objects come together, okay, there's a yeah, they come together and then they collide, right? They collide possibly at some angle, right? Um, some angle like this. And basically what happens is that if we think of, if we look closely at the four equations over here, right? So UA, VA, UA, VA, right? UA and VA have the same length, right? So essentially this means that VA, suppose is in some direction, VA. We can always find a plane, we can always find a line, right? If it's 2D, we can always find a line that is such that it looks as if, right? We can draw a line through the point of collision such that it looks as if the first ball A, bounced off a wall, right? And likewise for B, right? UB, right? If UB was this direction, we know VB is, number one, VB is the same length as UB, right? That's our equation 113 over here. UB is the same length as VB. And second important thing to note is that VB is parallel or anti-parallel to VA. So if we know the direction of VA, VB must lie along this line. So this equation, right, comparing VB with VA tells me the direction of VB, right? And comparing UB with VB, right, tells me the magnitude for VB. So essentially, the result is that, right, for 2D elastic collisions, right? If this even holds for 3D, right? For 2D and for 2D elastic collisions, when the two objects bounce off each other, right? By the fact that they are, by the fact that the magnitudes of velocities must be the same, as well as the fact that before and after the collision, right, their velocities must be parallel with one another. That means in the center of momentum frame, it looks as if the two objects, right, just bounce off an imaginary wall. Because if we draw an imaginary wall through the point of collision, right, we can see that if we draw an imaginary wall through the point of collision, um, if we replace, right, if we pretended that we forgot that the second object existed, right, and we just pretended that we threw the A towards a wall and bounced off this infinitely massive wall, then it would it would in fact behave like it bounced off a wall. And likewise, if we did the same thing but for B, where then we'll realize that it's as if B bounced off a wall, right? If we replaced presence of A with just a hard wall, the trajectory of B wouldn't be any different. So the upshot of this is that through the center of momentum frame, right, we've arrived at a very, very nice geometrical picture for 2D elastic collisions. And this nice geometrical picture, remember this only holds in the center of momentum frame, but this nice geometrical picture would help us with some questions a lot. Okay, so that's what we're going to talk about next.